Thank you so much. I'm really honored to be here with all of you in San Diego. In fact, I just came back from Singapore, so I'm a little bit jet lagged. And what you may not realize, especially looking at the weather out here, that you're actually in ground zero of the topic of water reuse, which is mainly what I'm going to talk about. That is recycling the wastewater back to drinking water. And when we talk about water contamination, I think you can look at this as maybe the most extreme possible case. So Jacques Cousteau said, we forget that the water cycle and the life cycle are one. And indeed, people get very passionate about water. And when we get into this topic of recycling water, I've seen meetings, public meetings, where they had to drag people out screaming, search us for weapons. I mean, people get very, very passionate about water. So the question is this tap water safe to drink? And this is the hardest question you'll ever get. I spent 10 years working for one of the larger water agencies in the United States, and when someone asks, is it safe or not, that's the hardest question. And you know what we answer? We always say it's compliant. A smart water utility will not say it's safe. And if you look at the news media, you would come to the conclusion that perhaps we are in a bit of a risky scenario. Water unsafe levels of industrial chemicals for 6 million Americans, around perfluorinated organics, and you're going to hear more later, I believe, on what happened in Flint. And as part of the EPA Science Advisory Board, I can tell you that within the EPA, we've been told that was a game changer that'll probably last for eternity. And there are other stories. How about the Wall Street Journal and Legionnaire's disease? Legionnaire's disease is definitely tied to water. Generally, as we try to reduce chlorine levels and we recirculate water in cooling systems, we have the propensity to grow pathogens, water-based pathogens, and of course, Legionnaire's is one of them. Deadly brain amoeba infects U.S. tap water for the first time, a topic which we thought was really limited to private wells in warm climates, discovered in the tap water in New Orleans. And the area where I've worked the most is endocrine disruption, or chemicals that enter the environment that can mimic the body, the organism's natural endocrine system. And of course, the media takes some great spins on this. My favorite, fish on drugs, more likely to drop out of school. So it's not so surprising that people don't trust tap water. In Southern California, about 80% of the public does not drink the tap water. And from a sustainability and energy standpoint, we start to wonder, well, why do we put so much energy into making pure water if no one drinks it? And we'll get into that. Now, I saw this quote, I think in Michael's, but attributed to an earlier one. I had to check that, but I had always thought it was Ben Franklin. But we see a game changer as we hit epic droughts. This is 2010 Wall Street Journal. And Atlanta, home of Coca-Cola, had trouble with a drought. And of course, Tucson and Phoenix in Arizona. And number one, Los Angeles. Big cities, big economies that are impacted by the ability to get water. In fact, as I said, California has taken some of the most progressive stands on this in the entire country, maybe in the entire world. 2013, the governor of California says that the state must pursue recycled water. The final sentence, California needs more high-quality water. Recycling is the key to getting there. When I was a student, I would have never guessed I'd see this in my lifetime, the governor of the state of California mandating the development of converting wastewater to drinking water. So how do we do it? We can do it directly. That's the topic of the day. And that is going from wastewater through advanced engineering processes and into drinking water. In California, Santa Clara Valley Water District in Silicon Valley is looking at this, several others. And indirect reuse, where we put it in the ground or we put it in a reservoir. Now, the indirect side, it's kind of like going to the dry cleaner with your best clothing, super clean, rolling around in the dirt because you want it to be natural. There is no scientific reason to do that. It's purely perception. So the scientists, we think we can do this. We have the technology, the engineering. However, the social sciences side is a little more delicate, the public perception. So I told you I spent a lot of time in Singapore. and no country has taken the bounds of Singapore. In fact, Lee Kuan Yew said every policy of their country had to bend to the needs of water survival. As they imported their water from Malaysia, and during World War II, as that water supply was threatened, in fact, that's one of the reasons they surrendered. Now, if you're trying to figure out what contaminants can be in water, I got an easy solution for you. Just assume everything. In wastewater, things go down the drain, things seep into the system, stormwater perhaps runs in. If we assume that essentially any product from nanotechnology to viruses to prions could be there, we can engineer multi-barrier systems that cope with these different types and classes of pathogens and chemicals. Now I want to make sure you understand, I'm sure everyone here does. Biologics have to come first. These are acute risks. Single exposure could lead to illness, could lead to death, and as you saw earlier, it still happens. So we have to get disinfection under control first before we worry about the chemicals. In the chemical world, we're talking about chronic risks, generally lifetime exposure, long-term exposure, and more endpoints that are very serious like cancer, but not from single doses, but rather from chronic exposure. In the United States, we have a long history of regulation, some of the longest in the world, dating back to 1899, when we were beginning to look at pollution in our river systems and discharges, and how do we control this for interstate commerce. Evolved through the 1914, 1962 with the Public Health Service. I find it fascinating that the Public Health Service began to regulate distribution system water in 1942. And of course, today we primarily deal with the Safe Drinking Water Act and the Clean Water Act. And these give the EPA empowerment to enforce rules, which is often delegated to the state. So most of my public speaking is actually in foreign countries. And you know, it's so amazing. We have, 300 million people who follow EPA rules. We have about 6 billion people who follow the WHO. So it's also important when you're outside the United States. But the process is generally the same. We look at this universe, all these possible chemicals. I work for the WHO, and WHO, the United Nations member states, will nominate chemicals. We see how much is there, how frequently. We look at the human health data, how potent is the substance, and how severe is the endpoint. Then we make a prioritization. For the EPA, they set a maximum contaminant limit goal. Many of you may not realize that. Look at that sometime, because sometimes that goal is 0. And as a chemist, that number 0 is really tricky to achieve. WHO does not promulgate rules, they promulgate guidance values. However, the vast majority of the UN member nations will actually use those as law. In the United States, we actually come up with a maximum contaminant limit, which is based on cost benefit. It is not based just on safety. So we have to be very careful when we're speaking about an MCL, because perhaps it was limited by the analytical detection limit or the cost to achieve. Conventional paradigm, what do we do? How do we get to these safe, if you will, numbers? Generally, we use a mammalian study. We use a very high dose of a chemical. We divide by uncertainty factors, 30 to 3,000. I've seen some divided by 30,000. If you're dividing by 30,000, you basically know nothing. We assume 2 liters a day consumption. We assume 70 kilograms of body weight. And what you may not realize, we assume that 80% of the exposure is not from water. Not from water. That makes a factor of 5. So we divide the number that would be, if you will, safe by 5, because we assume 80% of the chemical comes from somewhere else. The future question is, if 80% comes from somewhere else, is water where we should be putting our resources? That's a very political question. So I don't want to spend a lot of time on this, but in my classes I like to ask questions. You know, what was the first synthetic chemical ever industrially produced? It's actually the dye called mauve by Perkin. And Perkin discovered this by accident when he was a student. My favorite part of the story is he didn't tell his advisor. In fact, he went and patented it on his own and became very rich. So it's a very irritating story for me, but fascinating. First synthetic pharmaceutical industrially produced. Aspirin by Bayer in Germany. So our history of synthetic chemistry actually isn't that long if you think about human development. But how many chemicals do we have now? Well, the last time I looked, Chem Abstract said about 123 million chemical structures are known. So from a regulatory standpoint, this is an unachievable goal to try to find out the safety of every possible chemical. And what becomes even more daunting is when you think about the fact you are never exposed to one chemical at a time, you will always be exposed to a mixture. And how does that mixture interact with the body? Analytically, we can detect anything, anywhere. These instruments are absolutely amazing. We have instruments capable of measuring femtograms of a chemical in water, 10 to the minus 12th of a gram, unimaginable load levels. The question is, are we looking at the right things? Are we spinning our wheels looking at trace amounts of caffeine in water? That's ridiculous. But that's what we do. So I think this ties to Albert Einstein, who said, not everything that can be counted counts, and not everything that counts can be counted. Very, very true in water safety. Oops. I think I hit the wrong button. What did I do? No. Oops. Sorry, guys. I just blew it. I got it. There we go. All right. So what we're talking about is how do we look at water more comprehensively and think about not only the stuff we know about, that's targeted quantification, very, very straightforward, great analytical capacity, measuring things extremely accurately and at very low levels. But the area I want to get into is this idea of non-targeted screening, the things we don't know about, the next generation of substances. I think Professor Cummings is going to talk about disinfection byproducts. We only know the identity of maybe 30% of all the byproducts in water. So how do we do that? We can do it with high-resolution mass spectrometry, but I want to talk to you about high-throughput cell bioassays. That is a debate raging in this state, in California. I've heard that the California Water Board is going to put forward a couple $1 million to study this exact topic. Can we use human cell in vitro bioassays to monitor water safety? I'm going to get into that. So in the state of California, for the water reuse testing, I was part of an expert panel, and we said, how would you do this with this daunting mixture? And we said, there's really 3 tiers. Tier 1 are things you can measure fast. Because one thing you don't have in direct potable reuse is time. So what this means are online sensors, multiple redundant sensors on each unit process of the treatment plant that can alarm you if the process is running out of control within a certain boundary condition and alert the operators or even autonomously shut down the system. Tier 2 is pretty much what we do today. We take samples every so often with some frequency of indicator species of chemicals. We make sure that they're within the boundary conditions that we set. And by doing that, we can assure ourselves of a broader range of the universe of chemistry. But Tier 3 is the most interesting. This is where we get into high throughput in vitro screening. We're also working on embryonic developmental assays, mainly with zebrafish, also with xenopus, with frogs, and then non-targeted analytical. So I'm going to quickly now, in the remaining time, just show you how it works. Activated carbon, fantastic technology. By the way, extremely energy intensive. May not seem like it, but to make activated carbon takes a lot of energy. And what I'm showing you here, I know many of you probably aren't familiar with this, the water will fluoresce when it has carbon in it, when it has natural organic matter. So the influent from the recycled water plant has a lot of fluorescence. The BV is the bed volumes, how much water has passed through that carbon. So what you see is as the water passes through the carbon over time, the carbon begins to wear out. You see the fluorescence coming back. What we can do with that is build algorithms that we can control in a computer system that can look at how much fluorescence has passed through that carbon bed and back calculate the type of organic structures that would have been removed. And it allows us to know when that carbon is exhausted, when to regenerate it, on time in real time. I'll show you the same thing for ozone, powerful disinfectant, great for contaminant removal. Same idea. The water coming in, I call it the control. You can see the fluorescence as we add ozone, it oxidizes, and we can calculate through modeling how much of the chemicals are removed, and we can also calculate how much disinfection is happening, and if something goes wrong with the system, we can know within microseconds. We know instantly something went wrong. So we build these online real-time sensor networks to help with the operators. We've even talked about maybe we should make it available on the web to the consumer. They can see that the water is being purified real-time all the time. Indicators, the next section. When we begin to look at this world of 123 million chemicals, you can't get your mind around how you would measure all of them. So we try to prioritize which are the indicator species that tell us something about the treatment. They may not have any toxicity relevance, but they tell us a lot about the engineering. So in wastewater treatment, you either absorb, you bind something, or you biodegrade. And chemicals that don't biodegrade very well and don't absorb go right through the wastewater plant, like sucralose, the artificial sweetener. Fantastic marker. Toxic to humans? I sure hope not. I doubt it. But it's a fantastic marker for the treatment. We have now moved towards this suite of indicators where instead of a liter of water, we go to 1.5 milliliters of water, and today we need 100 microliters of water to measure nanograms per liter of these emerging indicator substances. And once we have that, we can do a lot of monitoring because it's fast. And this was published a couple years back where we looked at the different indicators. You can see sucralose was actually the most frequently detected in parts per billion range. And things like the estrogens we quite rarely detect in a very low levels. So this helps us prioritize the monitoring. So we have indicators of wastewater influence, and we have indicators of process failure. If we see the level of caffeine or the level of ibuprofen rise in a wastewater plant, that means something's not working. Something went awry in that biological process, so it's not working the way it should. The final case study, remember Tier 3, is bioassays and non-targeted analyses. I'm just going to show you one example from a publication we had in Environmental Science and Technology last year on glucocorticoids. And without getting deep into this, what we were doing, we were looking at transient transfection assays. These are human cells, endogenous genes, and we can essentially map the entire human genome. We can extract the chemicals from water, we can expose them to cells, and we can look at essentially all the genes in the human body. So I'm showing you just one example for endocrine disruptors. GR is glucocorticoid. If you don't know what that is, think about cortisone, progesterone, a lot of the anti-inflammatories. Androgen, male hormones, estrogen, female hormones. And the bottom line here is we don't really see that much estrogenicity anymore. When I was a student, it was pretty prevalent, but today's wastewater plants have gotten a lot better. But the glucocorticoid was shocking. We were absolutely dumbfounded. It's a log2 scale, so these were really high levels of glucocorticoid activity from a human cell. So we looked deeper. Well, why would that be? Well, in fact, I didn't realize that the amount of glucocorticoids prescribed are quite high. Among the most prescribed drugs, among the most in volume and in prescription volume. And here's the interesting part of the story. In 2014, the FDA approved the use of Flonase and Nasacort as over-the-counter drugs. If you go to Costco, you will see pallets of this stuff. In fact, I use it every day. I have some up in my room at this very hotel. So I'm part of the problem, I suppose. But very effective and very, very powerful, as you're about to see. In Tucson, we recycle our water in different ways, but one of the ways we do it, we discharge it into a dry riverbed, and that water flows to the north towards Phoenix. We think it's appropriate that our sewage goes to Phoenix, by the way. So as it's going up, we actually have wells along this river of wastewater, and we recycle it back to drinking water. this is the glucocorticoid cellular activity in the human cells. Now what we do, we use a positive control. The positive control in this case is dexamethasone, what we thought was the most powerful glucocorticoid. Previous studies, many studies used dexamethasone as the positive control. So we take the activity in the human cell and we equate that to dexamethasone equivalent units. So the two outfalls, there's two places where wastewater is being discharged. You can see the rise in glucocorticoid activity. As the river flows to the north through natural attenuation, the concentrations drop. But what was it? We didn't know. And no publication in scientific literature could explain it. Nobody had identified the substances that were causing or could account for all of that activity. So we applied everything I talked about, again, at high speed, high-resolution mass spectrometry. We did targeted analyses of all the glucocorticoid standards we could find, measuring down into parts per quadrillion. And what we found was that we see two different patterns. We see patterns of the substances that occur at higher concentrations, and we see some that occur at very, very low concentrations. But that doesn't tell you about the biological activity. That's half the equation, remember? That's just the occurrence. So in order to figure out, does that occurrence account for the biological activity, we had to test each of the glucocorticoid standards within the cell assay by itself. This is to get to the potency. Now this is in a logarithmic scale. And what we start to see, and it's probably not surprising, is that the synthetic forms of the glucocorticoid compounds are much, much more potent than are the natural. And part of that is pharmacokinetics. They're built to withstand the body. They're built to go into your body, absorb, and transport. So our dexamethasone, now if you remember what I said at the top of that red box, that was our gold standard. That's what we used, and that's why the relative effective potency is listed as 1. We normalized. But what we didn't know is that the active ingredient in Flonase was 71 times more powerful than what we thought was the positive control, at least within the in vitro bioassay. So the last part is, can we balance the budget? We have analytical data, we have human cell data. Does it match? And if it does, that means we figured it out. And again, it had never been done before in any scientific literature. People reported the activity, people reported some of the chemicals, but they did not balance. So through all this work, non-targeted analysis, and beginning to look at water treatment, we actually found that we were able to close that gap. We were able to identify substances, especially the Flonase ingredients, that had never been reported before in literature. Now, they don't match exactly. The black line is the chemical calculation. You add all the chemicals together, you look at their potency, that's what the numbers should be. The slashed or dotted line is what the human cell bioassay told us. But this is, within biological and chemical analysis, extraordinarily good matches. So in fact, the chemicals we were able to identify through analytical means, mainly starting with non-targeted high-resolution mass, compared to the effects in an endogenous human cell, actually matched each other. The other thing that was very interesting here, I'll just point it out because I actually have 1 minute left, is that chlorine doesn't work. It's a very unusual substance. It really surprised us. We've done many studies since then, but chlorine doesn't work that great. Even ozone, which is very powerful, not that great. But they are extremely susceptible to UV light. Even the smallest amount of ultraviolet light breaks them down. So now we know from an engineering standpoint, if we have to remove them, if someone calculates risk to the ecosystem, I doubt it's a human health issue at those levels, but we now have that knowledge of how to build the engineered system. We won't waste our energy on the ozone, we won't waste our energy on chlorine for these compounds, but UV would work very well. So in closing, Galileo, all truths are easy to understand once they're discovered. The point is to discover them. And the current paradigm for regulating in the United States is broken. We discover about 15,000 new substances per day. And the regulatory process of injecting a rat with very high doses of chemicals is expensive. It's animal rights issues for some people. And we will never catch up. We will be behind forever. So these new tools, in vitro, high-speed screening, we think is the path forward. And we think California will be the first state to do it, and the rest of the country will probably follow. So with that, I acknowledge my research group. Actually, as you might imagine, I don't do any of the work. I just get to talk about it. My students are hopefully back there working right now. And we have a great partner in Agilent Technologies for the analytical instruments. So thank you again for your attention, and take questions later.